Hi students. Now in today's lecture we will go through what is a semi-batch reactor, right? In this lecture we will see, first we'll talk about in general what is a semi-batch reactor. Then we'll see what type of reactions are generally done in semi-batch reactor, right? And we'll understand how semi-batch reactor will help us to achieve the high concentration of product, right? How it will help us to increase the productivity of a reaction by increasing the concentration of desired product. Then we'll look at the mole balance equations, right, in case of semi-batch reactors, right? We'll write down the mole balance equation in terms of conversion and then in terms of concentration. In this lecture, first we'll write down the mole balance equation in terms of your concentration, right? And maybe in another lecture we'll look at how to write down the equation in terms of conversion, right? So semi-batch reactor, firstly, as the names, we know what is a batch reactor, right? Where, if you remember, we have done this earlier, where nothing is flowing in, nothing is flowing out, right? Reactants are mixed up, right? They are kept for a certain period of time in a batch reactor. Remember, nothing is flowing in, nothing is flowing out, right? So in semi-batch reactor, either a reactant is coming in, right? Either the reactor, because it is a semi-batch, right? Either the reactant is flowing in the semi-batch reactor or a product is moving out or flowing out of the semi-batch reactor, right? Because it is not a batch reactor, so it's not like the reactants and products are not moving in and out. Either the reactant is moving in or the reactant is moving out, right? So basically, what type of reactions are these where reactant is moving in or product is moving out? Those types of reactions we'll carry out in a semi-batch reactor, right? So mainly semi-batch reactor is used for, first, to increase the selectivity, right? To increase the selectivity of a reaction. Increase the selectivity, right? What kind of reactions where we increase the selectivity using, we'll understand what is selectivity exactly. What kind of reactions are where we will be increasing the selectivity using semi-batch reaction? Ammonolysis and your chlorination. Mainly we carry out liquid phase reactions in your semi-batch reactor, right? Liquid phase reactions are done in semi-batch reactor. Second type is your reactive distillation. Reactive distillation, for example, esterification, right, is done in a semi-batch reactor using reactive distillation. What is this? We will see in a moment. Esterification. First, increase the selectivity. For example, we are carrying out a reaction, right, wherein two reactants A and B are reacting to give you a product, right? Say a product D, right, which is the desired product. And at the same time, in parallel, another reaction is going on wherein the same reactants A and B are reacting to give you an undesired product which is not required, say U, right? Now, by saying that semi-batch reactor helps to increase the selectivity, it means that it will help us to lower down the rate of reaction that is giving you an undesired product, right? So that undesired product is formed in a very lesser or minimal quantity, minimal or no quantity, or your desired product is formed in a larger quantity, right? This is your selectivity, and we'll look into selectivity in a mathematical form also, because our selectivity is mainly calculated using the rate of two reactions. One reaction which is giving you desired product, the other which is giving you undesired product, right? Then using selectivity ratio, selectivity, which is a ratio of rate of reaction of two reactions. Using the ratio, we'll see how to make the two reactants react, right, so that undesired product is formed in a lesser quantity or no quantity, right. Then you have a reactive distillation. Reactive distillation will carry out reactions such as esterification, and we know esterification is where acid will react with the alcohol to give you ester and water, right. And we know it is a reversible reaction, and if you remove one of the products, say water, right, then the rate of reaction will move towards product side, right. So how will you remove water, right? This reaction, if carried out in a semi-batch reactor, because in semi-batch reactor, I just mentioned earlier that either the reactant is moving in or the product is leaving the reactor. So here product water will leave the reactor, and how will it leave the reactor? We will vaporize water, right? Because it has a different boiling point as compared to the other product. So water will leave the reactor, will vaporize water, right? Now we'll see both. Let's talk about we'll now understand reactivity mathematically. A, right, is reacting with B to give you desired product D. Rate of this reaction is RD. A and B at the same time is giving you undesired product U, right? Rate of this reaction is RU, rate of this reaction is RD. Now if you apply rate law, right, like what we used to do in chemical kinetics, as per rate law, RD is equals to rate constant of this reaction is KD CA square CB. For this, RU is equals to KU CA CB square, right? Now, like I said earlier, selectivity is your ratio of rate RD and RU. Ratio of rate of this reaction and rate of this reaction. CA square upon CA CB upon CB square, right, is equals to KD upon KU CA upon CB, right. Now using this equation, what do you think about this reaction, right? Using this ratio, these two are constants, CA upon CB. Now selectivity ratio says selectivity of this reaction is directly proportional to concentration of A and inversely proportional to concentration of B, right? That means selectivity of this reaction can be increased by increasing the concentration of reactant A or decreasing the concentration of reactant B. Right now we need to carry out this reaction in a semi-batch reactor. How will semi-batch reactor will help us to achieve this selectivity? Right? How can we increase the concentration of A or decrease the concentration of B using semi-batch reactor? Let's look into this. This is your, say, semi-batch reactor. Right? Let's say this is your semi-batch reactor, right? Now you have to decrease the concentration of B, increase the concentration of A. Let's say you already have A, right, in your semi-batch reactor, and like I said in the beginning, either you have reactant flowing in or product leaving the semi-batch reactor, right? So you can decrease the concentration of B by slowly adding reactant B to the reactor that already contains your reactant A, right? So your B is added slowly to your semi-batch reactor. Using this technique or using this reactor, you can minimize the rate of this reaction that is giving you an undesired product. Right? I hope this is easy to understand. Right? So how will you increase the selectivity of this reaction? By adding reactant B slowly to reactant A, which is already there in your semi-batch reactor. Right? And now from this, the definition or the understanding of semi-batch reactor is also clear, that one of the reactant is flowing in, nothing is flowing out. Right? Now let's look at the other reactive distillation, esterification. Suppose again we have this, a semi-batch reactor. Right? Now here both reactants, that is esterification. In esterification you have reactant, this is your reaction, CH3COOH plus C2H5OH. This is a reversible reaction that gives you CH3COOC2H5 plus water. Right? Now this is a reversible reaction where if you remove water, right, if you remove water from this reaction, then this will help you to achieve the reaction going towards product side. Right? It will increase the concentration of this product. How will semi-batch reactor will help us to do this? You have acetic acid and ethanol in this, right, that are reacting to give you ester and your water. Right? So you have water also inside. Now what you can do is, using semi-batch reactor, you can vaporize this water. Right? Because water has a different boiling point. So water, you will vaporize water in order to remove it from the reactor. Right? So you will vaporize water. Right? So if you vaporize water, this water is removed. This water is removed from the reactor by vaporizing it. Right? So when water is removed, this reaction will move towards reactant side. Right? This is how semi-batch reactor will help us to achieve high concentration of reactant using reactive distillation. Right? I hope this is clear. This thing is also clear. Now we'll do mole balance. Right? Mole balance, will do mole balance using this selectivity example. We'll carry out mole balance on A, we'll carry out mole balance on B, then we'll write down the equation in terms of concentration. Right? So mole balance in terms of concentration, and in another next lecture we'll see mole balance for semi-batch reactor in terms of conversion. Mole balance in terms of concentration. Right here, first we will do mole balance on reactant A. Right? Mole balance on reactant A. We know that as per the general mole balance equation that we have done in the beginning, in minus out plus rate of plus generation is equals to accumulation. Right? Everyone knows this. Now in this, what is coming in, what is going out? Your reactant B is coming in. So if we carry out mole balance on reactant A, so we'll only be looking at A. A is neither flowing in, either A is not coming in, not going out. So in and out for A is 0. Right? Plus generation would be RAV is equals to accumulation, change in the number of moles of A with time. Right? Now we know that concentration is equals to moles, let's use N, moles per unit volume. Right? This is the formula. Now RA V is equals to D CAV upon dt is equals to CA dV upon dt plus V dCA upon dt. Right? Now we know that volume, right, since your reactant is flowing in, right, your B, this is flowing in, so volume is changing with time inside the reactor, right? So we say this volume is changing with time. Volume, that is, which is a function of T, Vt, volume is changing with time, right? So we need to find out the value of this, right, dV upon dt, right? So since the reactor is being filled, we said that V varies with time, right? Your volume is changing with, volume inside the reactor is changing with time, right? So Vt, now we need to calculate volume. This is calculated using overall mass balance. We need to do now mass balance on all species, remember, on all A and B and everything, on all species, right? Now we are doing mass balance, right? So we'll be following the same equation, instead of mole balance, now we'll call it as mass balance equation. In out plus generation is equals to accumulation, right? So we know that the formula for density is equals to mass per unit volume, right? Now if something is flowing in, right, we'll be taking this volume would be the volumetric flow rate, right? So now let's apply it on the overall, because nothing is going out, flowing in, right? So your density would vary rho 0. Let's say that the density of the system is rho 0, right? And the flow rate, this nu would be, this volume would be the volumetric flow rate, how much volume is flowing in at any time t, right, at any position at point A, say, right? This is using this formula, it would be rho 0 nu 0 minus out, nothing is flowing out, 0, right, plus generation, it would be 0, right? Mass is equals to mass balance. So rate of change of, we are doing mass balance, so here we were doing mole balance, so rate of change of moles with time. So here rate of change of mass with time, and mass is density per unit volume, right? So it would be rho V, like this, right? This is your mass balance equation. Now for systems that have constant density means rho is equals to rho 0, right? So your nu 0 would be equal to dV upon dt, right? This is the value of your rho 0, volumetric flow rate, right? Now we will substitute this value in this equation, right? Let's see what we will get. Right, first let's solve this equation first. Right, we can solve this equation, we can integrate it. Right, it would be dV is equals to nu 0 dt. Now if you integrate this, you will get V is equals to nu 0 t plus C. Right, now to find the value of constant at t is equals to 0, right, at t is equals to 0, let's say volume is equals to V0, therefore C is equals to, volume is equals to V0, this would be V0, therefore this equation will become V is equals to nu 0 t plus V0. This is the equation. right? I hope this much is clear. Now we'll put the value of dV upon dt in this equation, right? Let's put the value of dV upon dt in this equation. I'll just rub this off. Now let's quickly do this. We'll put the value of this dV upon dt here, right? So what we will get is RAV is equals to CA nu 0 plus V dCA upon dt, right? Now what you will do is you will divide this equation by V, right? You will divide this equation by dividing by V, so it will become V dCA upon, it will become dCA upon dt plus nu 0 upon V CA plus equal to RA. This is the equation that has become, right? Now this equation can be solved using polymath, right? If you know, these are the concepts that you should know, but in your actual calculations this equation can be solved using ODE, right? Polymath, which we will see in some other lecture, right? These are differential equations. Right? So you can take all these things down. Right? You can take all these things down. This is a differential equation. I'll just write it over here. This can be solved using ODE solver. Right? I hope this much is clear. It's a simple equation. Right? First we did mole balance on A. Right? Then we know that volume is changing with time, right? Here volume is changing with time, so in order to find volume at any time t, we did overall mass balance on overall, right? So in minus out, nothing is going out, the overall rate of change of mass would be rho v dt. For constant density both would be equal to 0. This equation has changed to this. We integrated it, we got this. We'll be using this equation in a moment, we'll see. So we substituted the value of dV upon dt in this equation, right? And we got this, right? I hope this much is clear. Now we'll do mole balance on species B, right? Now we'll do mole balance on species B quickly. Mole balance on species B, just look at B. Now we have done something known as flow rate. It's flowing inside the reactor, semi-batch reactor, right? So we will be using flow rate. In minus out, in, since B is flowing in, so we will be using FB0. We'll be using one that we have already, I've just rubbed that off. Mole balance on B, on reactant B. So in minus out plus generation is equals to accumulation, right? In would be, B is moving in, so its rate of flow would be FB0. FB0 minus out 0, right? Then your generation term would be RVV, right? And what would be the accumulation? Accumulation, like we did earlier, right? Rate of change of moles of B. upon dt. Right? This is simple. So we know that concentration is equals to moles per unit volume. So in place of NB we will write CV upon dt. Right, C would be, let's write it as CB, concentration of B, just to specify we are doing it on B. Right, and this is your flow rate, right, molar flow rate. We know that it's just like moles. Since the system is in flow, we have done this earlier also. Since the system is in flow, so we will take it as molar flow rate. If this is your flow rate, say at this point, what is the flow rate? How many moles are passing at this point? This is your FB. This is your FB, molar flow rate. Right? When contents are flowing, then to find how many moles are passing through a point, at any point, say A, right? Then we use the term molar flow rate, denoted by FB0. Right, FB0 are the number of moles, right, passing through this point, right? So, and if FB0, this is the number of moles passing, then there must be some concentration that is passing, right? Or what is the volumetric flow rate? So concentration would be equal to molar flow rate upon volumetric flow rate for systems that are in motion, therefore systems that are flowing. Right, so your FB0 upon nu 0 is equals to C. So FB0 would be equal to C nu 0. Right, FB0 would be equal to C nu 0. You will substitute the value of here. Right, let's say C for CB0 nu 0 from here plus RB V equal to, now here we'll have to again solve it, V dCB upon dt plus CB dV upon dt. This is the equation, right? This is the equation, and now we will be using right, so this is your right, this is something you've got. Now if you remember, we have done this when we were doing mole balance on A. We got this equation, V is equals to nu 0 plus V0 nu 0 T, right? You can just look back, right? You can just rewind the video and you will find this equation, right? I said there I will be using this equation. Now we will be substituting the value of V in this equation, right? And then differentiating. If you substitute the value of this V in this equation and then differentiate, what you will get is dCB upon dt, right? dCB upon dt is equals to RB plus nu 0 CB0 minus CB upon V, so volume. This is the equation that you will get. I repeat, you substitute the value of V in this equation and then differentiate, right? I'll just write substituting V, say this is equation 2, in equation 2 and differentiating, right? You will get this equation. Right, now this equation can be solved like there at using, these are differential equations using ODE solver or ODE solver, right? We'll see that in some time, how we calculate these equations. So this is the equation, right, for semi-batch reactor in terms of concentration, right? You can